I know, make it a class on Thursday, right? I wonder if it's possible for we a class tomorrow. Via Zoom and what time?
I forgot to get back to you because there's been other students that start classes. I'm not sure what time.
All right, no
Maybe
worries.
by the end of the class.
Sure, so I got say one class tomorrow.
If we could do a remote class tomorrow, yeah.
We get elective from 1 to 4.
Right. And 5 to 7 free.
Yeah, well,
Or you got this remote class, right? The Zoom class.
Yeah, we got nothing from 5 to 7.
I think we can start 5 to 12, right? And pushing our exchange. Right, so we can set for that tomorrow. We start about 5:30 instead of 6, so we could push in a little extra more. And we finish off early too, because you got class from 1, so it might be a little tired. So tomorrow we not do heavy theory. We just do some practice. It shouldn't be difficult. All right, good. So let me get started. So we do 2 things today. Today we can talk about IPv6 and BGP. Right, we talk about IPv6 and we talk about BGP. Right. All right. So first, we recap some things. So any device that communicates on a network must have an IP address. Now there are 2 types of IP addresses. First one is IPv4 address, or we shorthand say IP address, and the other is IPv6 address, right? The IPv4 address is stored 2 bits in length, right? And it is structured as follows: A.B.C.D, where A, B, C, and D are all 8 bits long each. Right? Now, something with 8 bits, if you write it out in binary 1, 2, 3, 4, 5, 6, 7, 8, the maximum value is 255. So that means your addresses could be from 0.0.0 all the way to 255.255.255.255. Right? Now, IPv4 addresses are divided into different categories based on the use case. So you could have public IP addresses and private IP addresses. All right. You could also have class A, B, C, D, E addresses. Then you could have unicast, multicast, and broadcast addresses. So different ways of classifying the IPv4 addresses, right? So let me look at and see what was the use case for each of them. So public IP addresses are routable on the public internet, right? Good. However, these IP addresses are in limited supply, right? Limited supply. Therefore, private IP addresses were introduced. Now, the private IP addresses are also divided into class A, B, and C. So let me get this and make sure I tell you the right thing. Right. So class A addresses in general is from 0 to 127. It starts with, right? 128 to 191. 192 to 223. Class D, which is multicast, is from 224 to 239. And class E, which is also multicast, is from 240 to 255. Now, the private IP addresses, right? Class A is from 10.0.0 to 10.255.255.0, which is 10.0.0/8. Then you got class B private IP addresses, which is 172.16.0.0/12, and class C 192.168.0.0/16. Right. So private IP address is also used in A, B, and C. So what's the difference between the two? Is that any agency is free to use any private IP addresses, right? However, for communication on the internet, at some point in the network, right, a device that performs network address translation must be used. So there's NAT, right? And NAT maps a private IP address to a public IP address. So it's like within a room, we just give persons names 1, 2, 3, 4, 5, 6, and then some other company they could use names 1, 2, 3, 4, 5, 6. But then to communicate, if those two agencies try and communicate to each other, it's not possible if everybody using the same names. They must got some name that is unique to them that's used for communication over a public medium. So that's what that does. Converts a private IP to a public IP address, right? Now, class A, B, C, D, and E addresses, it's just different categorizations for them, right? Based on what it starts with, right? But class D is a special, it's multicast address, just 224 to 239. It starts with 224 to 239. Now, what's the difference between unicast, multicast, and broadcast? So in unicast address, one device speaks to another device, right? So when it builds the IP packet, they're gonna set a source IP and a destination IP. So the source IP is his own IP, like 192.168.1.2. And the destination IP is the IP address for who is going to, which might be 192.168.1.3. Right, so this is unicast communication. Is two devices talking to each other, right? For example, me having a conversation with Mark and Dave, we talking to each other. So this is unicast. But multicast now is when one person, right, or a group of devices communicate amongst themselves to the exclusion of other devices. So if there are 14 persons in the class, right? Then multicast communication involves a select group of persons, right? So for example, if I want to talk to the class reps alone, then I might say class reps, please call me, right? Then the persons who are identified as class reps, they know themselves, right? So when I send a message, I can send it to the destination IP, gonna be a special address that only persons that are class reps can listen to it, right? So source IP gonna be 192.168.1.2, which is my IP, but the destination IP, right? The destination IP gonna be some multicast address 224.0.0.1, right? So once the class reps identify themselves as class reps, they can start listening on 224.0.0.1. Now, when you computer they got away, you could see what multicast addresses you're showing. So this is with IPv6, right? As long as you use a device, you listening in on these addresses here, right? So I can explain this later when we talk a little bit about IPv6, but I think IPv4 must got they got, so these are the addresses that I listening to on IPv4. Like 224.0.0.1, 224.0.0.251, and so on. So there's multicast address. Now broadcast address is when you talk to everybody, right? So if I say a message, class, please email me your USI. This is broadcast communication. So this for everybody on the network. So the source IP is usually 192.168.1.2, and the destination IP will be the broadcast address for the network 192.168.1.255. So it's usually the last IP in the subnet is the broadcast IP, right? So if a network is 192.168.1.0/24, it's going from 192.168.1.1 to 192.168.1.255. Right, so 255. Actually, we're from 0 to 255. And you got some special addresses. The 1.0 you call is the network address. 192.168.1.1. This is the forest address. 192.168.1.254. This is the last address, last usable address that you could assign to a user. And the last address, 192.168.1.255, is the broadcast address. Right. So these are different classifications of IPv4 address. Now, the problem is that IPv4, right? IPv4 addresses are in limited supply. And the reason for that is because to store the 2 bits, they only got how many different options that we can get. They only got 4 billion and change. They only got 4, let me see, 296 comma. So only 4 billion addresses are possible. I remember now we got 7 billion persons on Earth. But it's not only people communicate, right? It's devices communicate. And the average person got at least 2 devices, right? Most people got 2 devices, 3 devices. Then you got your TV, fridge, everything getting internet now. All these things need IP addresses, right? Especially with Internet of Things. So we learn Internet of Things in your second year course. As part of our research that you do. So because you got so many things that need addresses, right? Then you need solutions to deal with the exhaustion of IP addresses. So 2 solutions was to use NAT to introduce private IPv4 addresses. The other solution is to use IPv6, right? IPv6 addresses. Now, I'll show you how to set your IP address on your computer. You go Control Panel, Network and Internet, Network and Sharing Center. Change adapter settings. And internet cable, okay, unplug. Then you go Properties. So you're going IPv4, you're going the IPv6 settings, right? Right now I got it to obtain address automatically, but you could enter your IPv6 address inside it. Right? So those are your set your IPv6 address. So a computer could get if you get an IPv6 address only, if you get an IPv4 address only, or you can get an IPv4 and IPv6 address. You call it dual stop, right? Dual stop. So what we can learn today is about IPv6 addresses. Any questions so far?
Okay.
Very good. Okay. So we talk about IPv6 addresses now. So IPv6 addresses, this is the structure for it, right? So it takes some time for wrap your head around it. Don't worry. Instead of an IPv4 addresses, you got 4 groups of 8 bits each. In an IPv6 address, you got 8 groups with 16 bits each, right? 16 bits. So each number is a hexadecimal, right? So it's 8 groups, 1 group, 2 group, 3 group, 4 group, 5 group, 6, 7, 8 groups. And each bit, right? So you got 4 bits in a group. Each bit is each of these digits, if we want to call it, is 16 bits. Because the 16 bits, it could go from, and it's hexadecimal, it go from 0 to 9, and then 0 to 9, A, B, C, D, E, F, up to F. right? It go up to F. Good. Now, the force for 48 bits, right? The force for 48, so this is force for 48 bits, 16 and 16 and 16. Force for 48 bits, you call this the global prefix, right? So when you apply to the regional internet registry for an IPv6 address, they give you a subnet, right? Good. So this force part, this fix, this is for your organization. Then the following 16 bits is called the subnet parts. So there's this next 16 bits here. Good. And the last 64 bits, you call it the interface ID, right? You call it the interface ID. So let me show you hierarchically what this looks like. This is gonna blow your mind. These people mean for fix it, right? So from the RIR, right, you get 48 bits here, right? So this can't change. This can't change. Then at the next level now, right? At the next level, you get 16 bits to play with, right? You get 16 bits to play with. So you get 16 bits to play with. Now this 16 bits, right, means, right, you can create 2 to the 16th subnetworks, right? Or you see subnets, right? You could create 2 to the 16th subnets. So from this /48 you get 2 to the 16th is how much? 2 to the 16th power is 65,536, right? 65,536 different subnets. Good. And then, right, from each of those now, you got 64 bits to play with. You got 64 bits to play with. Right, so this makes up the unique part of the user address, right? The unique part of the user address. So from one network, so so let me map this here, like how we do 192.168.1.0/24. Good. How much bits you got for the users? 2 to the 8 bits. You could accommodate 254 users, right? But for one IPv6 network, you can accommodate 2 to the 64 number of users. So this is how much people we could get on this network. I don't even know what was this number. 1.8 by 10 to the minus 19. Right, 1.8 E plus 19. This is the amount of users you could have on this network. So you could get, from this one address, you could get 65,536 different networks, right? And in each of them network, you could get 2 to the 64 number of users. So let me multiply this, right? So we do 65,536 times 2 to the 6. Good. So you could get, right, from this one address that you get from the internet registry, you could accommodate 1.2. Now, let me do 24. This 1.2, 24. 1.2, 10 to 24 power. So if it's 3 is 6 is a million, right? 9 is a billion. So you could do 9, there's a billion. 9 is a billion, there's 18, right? A million, 1 million. So we could accommodate 1.2 million billion users for this /48, for this IPv6 subnet that's allocated to you. But what you gotta remember, this is only allocated to you agency, right? This /48 means, you know, you get 2 to the /48 different options. So 2 to the 48 is how much? It's 2.8 E to the 14 power. So 2.8 E to the 14 power. Let me see. There's you got the 3 there, a million. A billion is 9.
Trillion, sir.
A billion is 9. So there's 9 and 3, 12, and 2 zeros is how much, right? hold on. This is just 1 point. This is 3 and 3 is just this is just 1 million. 1 million billion views is a big number, right? And then almost a million billion different companies. So let me go back again now, right? So with IPv6, so remember IPv4, up to how much you could get? 4.9 billion, right? That's all. With IPv6, we could get up to 2.8 million billion different companies. And each of them companies could accommodate 1.2 million billion users. Right? So in summary, IPv6 has a lot of addresses. And I don't think we will be seeing IPv7 or IPv8 in our lifetime. So they solved the problem of addresses being exhausted. Now, what's the problem? Why IPv6 not so popular? All right. And I explain to you why it's not popular. But let me take a break and then we can have the discussion. Any questions so far?
No, sir.
All right, good. All right, let's continue. So the next question we want to discuss, right? Why isn't IPv6 prevalent, or why hasn't IPv6 completely replaced IPv4 addresses, right? And the answer for that is a lot of servers on the internet are not using IPv6. So there's one reason. And two, knowledge about IPv6 is not so widespread, right? And then the change from IPv4 to IPv6 is difficult. A lot of reconfigurations have to be done. Companies are blocked out. Right, so let me explain to you what the challenge would be. So let's say this cloud represents the internet. This now is your router. And you also got to choose the head. And this is some server on the internet that you want to reach to. And this is your DNS server. Right. So this is the internet. This is you, router. This is DNS server. This is let's say this is some website. So this is the web server that you want to reach, right? And this web server got an IP address 23.23.23.23. Your computer now, you actually give you a public IP 168.232.145.2. This is your public IP. And this is your DNS server. The DNS server is it. No, we gotta give you IPv6 address. So you say your address is 304:45:1. I explained to you what the ::1 is. Your DNS server is 2304:5:8. No, let me say the name for this web server is flixnet.com, right? www.flixnet.com. But no, what I'm gonna explain to you is what was the problem, right? What's the challenge we have with the internet? Now, when you computer, right, you type in your browser that you want to reach www.flixnet.com, right? Let me explain to you what is happening. This is the DNS process, right? This computer, right, he doesn't know what's the IP address for www.flixnet.com, right? So the computer does not know the IP address, right? In this case, the IPv6 address for www.flixnet.com. So when a computer doesn't know an IP address, it initiates, right, the DNS process, right? This means domain name service, right? So it will ask its DNS server, what is the IP address www.flixnet.com, right? But now, how does the computer know its DNS server? It knows the DNS server because you manually configure it, or it gets it via DHCP, right? So it either automatically gets this address via the process of DHCP, which we can look at in a class, or you statically put in the DNS. To know what DNS server your computer using, you could type nslookup, only put www.com, right? And they can tell you what's the name of your DNS server, right? And what's the address of your DNS server. In this case, my DNS server name, right, is 10.9.0.10. So everybody try this on your computer. Open command prompt, right? Open command prompt, and then type nslookup for any website that you want, right? And let me hear some responses from you. What's your DNS server, and if it work for the website that you want with the IP address? Go ahead and try.
Yes, sir. We got it. Server is
What's your DNS?
my DNS server is dsl.goal.net.ui.
What's the IP for it?
190.80.4.147.
Let's see. That 80.4.197.
That 147.
Okay, this is GTNT IP. So you could go on the internet and you can type the internet or look up IP before address. So put the IP here. And then you tell yes, it belongs. It is in Guyana. It's a Guyana IP. What information here from it? Who own it? So it comes from LACNIC. This is the regional internet registry. Okay, and who own it? Registrar, University of Vienna, CIT. Oh, interesting.
Pero naman
Registrant
got a
name.
mask. Look like you got a mask.
John Prasad. And they got other details from him. But it's GTNT, that's what I want to know. Yeah, registering John Prasad name. That is the name service. So you got a lot of information. All right. Good. Yeah, so that's the DNS process. So coming back to the example. Yeah. So it will access DNS server. We'll see IP to www.fixnet.com. Good. Now, the DNS server might not know, right, the IP address for www.fixnet.com. Right? So the DNS server will ask the root, right? Root DNS server. The root DNS server is dot, right? I'll show you how this entire DNS process is work. So your root DNS server now can ask another big and powerful server, right? So this is gonna be the root server. The one you got couple inside the world, right? The root DNS server. He's the boss, right? They got to think 13 of them, right? So how many root DNS servers are there? 13 root DNS server, right? But so the DNS server can ask the root DNS server. But the root DNS server now, the root DNS server does not know, right? Does not know www.flixnet.com. But the root server says, right, that I know .com. I know who get .com. So he will return the IP of the .com, right? DNS server, the .com DNS server. So when he returns the .com DNS server to you local DNS server now, you DNS server then asks the .com server. Right, so this is the .com server. Now, so your DNS server will ask the .com server for www.flixnet.com. All right. The .com server does not know, right? www.flixnet.com, right? The .com server knows, right? Who knows, right? Flixnet.com. So believe it or not, the www is actually something, right? Good. So what the .com server gonna do is tell you how to reach a next DNS server now, right? And I can tell you this DNS server now, he knows Flixnet.com. Or he know www.com server don't know www.flixnet.com. He know just Flixnet.com. So then now you can send you DNS request to Flixnet.com. So you can ask Flixnet.com, right? So your DNS server will ask Flixnet.com what is the IPv6 address of www.flixnet.com, right? And flixnet.com will reply and say that there is no IPv6 address for www.flixnet.com. Why? Because it's configured only with a 23.23.23.23, only with the IPv4 address. So finally, your DNS server will reply and tell you there is no IPv6 address for www.flixnet.com. So let me try NSLookup for something that don't exist. NSLookup lemuel.com. NSLookup lemuel.com. Most guys actually got to lemuel.com.
Wait, what?
So
Sir, I tell you to do
lemuel.com, right? I got your own website. All right, definitely got a SachinRamcharan.com. NSLookup SachinRamcharan.com. Don't tell me that. Good. You see, can't find SachinRamcharan.com. Non-existent domain. So ultimately, this is the answer that you will get. Right? So because you're using an IPv6 only address, and this server only get an IPv4 address, then you're not going to be able to browse to it. And the root, come back to the root problem, majority of the internet using, they ain't configure IPv6 on it. And as a result, you can't reach resources that you get. If you're using IPv6, right, you got something at IPv6 address, you can communicate with it, right? And those the kind of chicken and egg scenario. You don't get a lot of IPv6 because a lot of people are using IPv6. And a lot of people are using IPv6 address because, so you can't get IPv6 address because a lot of people ain't using it, right? Because a lot of people ain't using it because the users ain't using it, and you keep going around this, right? So those the problem that we get right now. However, they got agencies and they got people that working hard to ensure that that people going to adopt and use IPv6 address, right? They got a lot of reports on it. Blacknik just provide a lot of reports on usage for IPv6, right? So this is, so now I explained to you is the DNS process, right? Is the process that every DNS server does go through in order to find the address for something. At this stage, if you reach flixnet.com and it had an IPv6 address, it would return it to your DNS server, and then your DNS server would return it to you. I think you could check your DNS cache. Okay. Now R minus A is your R cache. Let's see. Check DNS cache. CNV. ipconfig/display DNS. So I got a lot of websites that I already go to Google for, and you see the cache. You keep a cache for it, right? So if I subsequently want to go and reach this website now, it now go to the DNS server, right? So let me say I browse to www.com, right? It's gonna maintain so the DNS server will go through these processes, so and then you can get the address and then return it to me. When I get the information now, I can put it inside me DNS cache, right? But the DNS cache is not forever. It got time to live. Here we could see is 182,000 seconds. When the 182,000 seconds gone, the record gonna move. And if I ask back for www.com, I gotta go through the entire process, right? So there's your cache here. All right, so that's the process of the DNS lookup, and that explains to you why IPv6 address is not often used. Let me look a little bit more the mechanics of IPv6. So IPv6 addresses consists of 8 groups of 16 bits. For 16 bits is the global prefix. Last 64 bits is called the interface ID. Now, some things about writing them. If you got like 4 zeros, right, in one group, you could just write 1 0 instead, like this, right? So when any computer or any router see a 0, they interpret it as being 4 0. So there's a way for sharpening the address. The next thing is, if you got consecutive blocks of zeros, like we got consecutive blocks of zeros here, then we could put 2 colon, right? So 2 colon means consecutive blocks of zeros. So we get 1, 2, 3, 4, 5, 6 groups. And because we got 2 colon here, and because it's 8 groups overall, 8 minus 6 is 2. So the computer can interpret this as being 2 consecutive rows of zeros. So these are some rules that you can use in order to for shorting an IPv6 address, right? So let me just do an example. Seriously. Well, yeah, it's straightforward. I don't know example. These are 1, 2, 3, 4, 4, and then we do a 1, 0, 1, 1, 2, 3, 4, 1, 2, 3, 4. So we can shorten this as, let me see, it's 8 okay here. 1, 2, 3, 4, 5, 6, 7, 8. Go. So I can shorten this as 2001. Sorry. I can write this as 2001 colon. I could remove the leading 0. So I could just write this as DB4. Then you put 3 CD3. Now this is 2 consecutive blocks of zeros. So I could put a colon here. And then I come to 0, 1, or 3. I could just write this as 1 or 3. Now the thing is, right? I can write back this as 2 colons, right? You can't write back this as 2 colons. Only one time you could do the double colon. So I can write this as 0 and 0. So this address, I could shorten it as this address here. Any questions? So you remove the leading 0. You replace any consecutive blocks of zeros with 2 colons, but you could only do it one time. So if it happened again, you gotta just write 1, 0 for represent the block. So they're good? They're good with you? Let me explain,
Sure,
and it's simple.
You could put a double colon anywhere in the line.
Anyway,
Like for
yeah,
example, you could have put 0, 0 there and double colon again.
Yeah, but let me show you a problem here, right? If we had 1, 2, 3, 4 more zeros here, right? And if we need to put a double colon there and a double colon there, right? The problem here is you don't know if the 3 zeros is on here this side or if the 3 zeros is on this side, right? That's why you could only do the double colon one time. So we got the option of writing this as 0, 0, 0, 0, and then use the double colon at the end, right? We could do this. Or we could use the double colon here, and then we put 0, colon, 0. So you could use the double colon anyone you want, but you could only use the double colon once. Good?
Yes, sir.
Yeah, so it's pretty straightforward. All right. So just like you got different types of IPv4 addresses, you got different types of IPv6 addresses, right? So you got the global addresses that use on the internet. So just kind of think of this as like public IPs, right? And those is from 2000 : /3, right? 2000 : /3. And those go all the way up to 3FFF, right? So the general practice is for agency get a /48 subnet, and then you get 16 bits to create you subnets for your agencies, and the last 64 bits is your unique host ID. So in we case and the MA case, we get 2803 : E340 : /32, right? So we get a lot of different networks that we can give the clients. Then we get a subnet plan. So when you get this big block now, right? Let me just show you the design process. When I get this big block now, then I gotta determine how I want do me subnetting plan, right? So in me addressing plan, I write this thing 2000. So this guy here, so write it for we do it. Ganesh is a bad man, and then I update it in 2023. But the man's the best. Yeah, so this is me subnet plan now, right? So out of the address I get, I decide which ones I want to use and for what purpose, right? So you just come up with the plan. What you're assigning for your customers, what you're assigning for links between routers, which you assigning to your agency alone, what you're assigning for monitor, and so on. So we got your own IPv6 plan here. And you use a tool like a IP address manager, right? So we got an IP address manager for manage, right? For manage the allocation of IP addresses. So this PHP IPAM, and then remember when you assign a subnet to one customer, then you don't want to reuse it, right? So for example, everything in 172.16.00/16, we subnetted further, and we gave them to different customers. So you don't get any overlap with the IPs. All right. So you get global addresses that routable over the entire internet. And then you get link local addresses, right? Now, link local addresses, what this means is that this you could only use this on your router interface. So link local addresses only could use on one router interface. And it starts with FE80. So between router 1, router 2, router 3, we could use FE80 : 1 here, and we could use FE80 : 2, and then I could use back FE80 : 1, and I could use back FE80 : 2. I can't put FE80 : 1 because these two are gonna overtalk to each other. I could use back the addresses because these addresses don't get routed, right? So you can use a routing protocol and advertise this address like what we do in OSPF. You can advertise link local addresses. Now you might ask yourself, well, why this useful, right? Why this useful? And it's because of a limitation with IPv4 in routing. So I can explain to the concept to you after we take a break, right? Why link local addresses? What problem it's solving, right? So it's important that we understand why for some of these things. And so we take a break and then we're gonna All right, let me continue. All right, so let me explain. So we want to explain, right, so that you can understand why link local addresses those be used, right, and what problem it's solving. But before we could go to the, let me go back to IPv4 and OSPF routing. So in IPv4 routing, you might get 4 routers doing OSPF like this, right? There are 4 routers doing network like this. So let me say this is network 1. Between these 2 devices, we got next network. Between these 2 devices, we might get next network. Between these 2 devices, we might get next network. Between these 2 devices, we got next network. And then here we got network 6, right? So in other words, here we got 6 different networks, 6 different subnets that use between these devices. Now, the main, right, the main purpose of the routing protocol is to advertise, right, the routes for users, right? However, configuration of OSPF N2, N4, N3, and N5 are also routed. But these are unnecessary, right? Unnecessary routes. Because N6 is only interested in reaching N1 and vice versa. Right? Now, these unnecessary routes, right, have an impact on computing and time to convergence right? So in other words, some amount of CPU on the router got used up to calculate these additional routes and build, right? Use Dijkstra's algorithm on all of these information and build a routing table. And if one of the links go down, you gotta run back Dijkstra's algorithm because you get a new topology, right? You get new topology. So you got 4 extra routes, right? That are necessary, right? You don't need to learn these via OSPF. So the only route you're really interested in exchanging via OSPF is N1 and N6. And these in between, they just facilitate in the routing protocol. They're not necessary. So the solution is now in IPv6 is to use link local addresses, right? Use link local addresses. And by using link local addresses, these don't get advertised in the routing protocol. Only the end addresses, right? Only the end addresses get advertised. So you save on computing power and your network able to converge much faster. Another thing is, right, by using link local addresses, you could automate the configuration of our router, right? Because for each router, right, if this is router 1, we can make all the interfaces FE80::1, FE80::1, FE80::1. This router, we can make all the interfaces FE80::2, FE80::2, and so on. This router, we can make all the interfaces FE80::3, FE80::3, and so on. So by doing this now, you simplify, right, and improve and increase the time for configure this IPv4. You gotta get a unique IP for each interface. So in we case, right, we gotta go into IPAM. And then we gotta look for address. So we usually go in transport and core network. And then we gotta look for unique IPs. So the time it takes to come document this IP that being used, and then go on your router and configure it, is time consuming. Versus with link local addresses, you just one thing for each of them. You name this router 72, and then you use 72. I remember how much options you got. You got enough options because 16 bits is 2 to the 16 power. Addresses, you can get 65,000 unique routers participating in it. Then when you think about reserving IP and everything like that, just configure things as fast as you can. Right? So that's the purpose of link local addresses, and that's the problem that it solves. So let me continue on. There are some other addresses, of course, multicast addresses, just like in IPv6, there are multicast. Multicast IPv4 addresses start with 224.00/4. This is the subnet for it. And a multicast is FF00::/8. So if you look at all these multicast addresses that's on the computer, The true interface IPv6 show join. You see everything starts with FF because these are our multicast addresses that need complete join. All right. So what we talk about now, right, is the EUI 64 identifier, right? This is a next improvement that you got in devices in order for to get IP addresses. So now we come on an IPv4 network. So IPv4 network now, you gotta get a plan, right? You gotta get a plan. So if you got we put a switch here, and then you connect like 5 or 6 users. Good. So if the subnet, right? If your subnet is 192.168.1.0/24, you can put the gateway as being 192.168.1.1. Now you gotta ensure, right, that if you got 100 users on your network, you gotta make sure that each of them use a unique IP. One that's fine. You gotta make sure that each address use something unique. So you gotta get like an IPAM, like how I got IPAM here. You gotta go in IPAM and you gotta document all of these, right? And you gotta make sure that two people don't use the same addresses. Now, in IPv6, they solve this problem because they got an automatic method for somebody get a unique IP. They use extended unique identifier, EUI 64. And they use the MAC address. The MAC address is a key component within the EUI 64 kind of setup. And why they use it? Because each network interface carries NIC, right? Supposed to get a unique MAC address, right? So by design, you already get a unique MAC address, so make that part of the address, and then ease onboarding from the network administrator for set up static IPs. So let me say that my device MAC address is 0060 D6731987. In order to farm the EUI 64 unique identifier. So this is the last 64 bits for your IPv6 address, right? In the middle, right? Split this in the middle between the D6 and the 73 and put FFFE, right? That's what you do it. And then the 7th bit, you change it to a 1, right? The 7th bit, you change it to a 1. So in my case, 00, 000, and then 60. This changes now to the 7th bit, right? So this 0 is 4 bits, and then this 0 here is the next 4 bits. So the 7th bit is inside the here. So you get 000 and then 0010. So this is the 7th bit, right? You change it to a 1. And this now, right, is your unique ID for this router, right? The unique the last 64 bits of the IP. This is the EUI 64 address. So this is how you get it. Now, Microsoft has masked your IPv6 address. So I don't know if I can see it here. Right, so there's mask address. So you might see it on your computer. But so what I mean by mask it, in order for cybersecurity purposes, they don't include it. But if you see, look, they got the FE in front here. So they kind of do, they kind of use it. Let me see what's MAC address. So this is 0389, and then they got the FFFE, and then they put just E9 here. Yeah, they mask this. You see this little star, this little thing. They mask this this IP. This is why you can't actually see it. But they got the FFFE here, and then they just mask it. So that's fine. But this is the so now forget the IP address, right? The last 64 bits, you gotta set it. You gotta do 1, 2, 3, 4, 5, 6, and so on, and count it up, right? The device can just automatically compute this, and by putting this address, it makes sure this don't conflict with nobody else. So you got a case where two people get the same IP address. All right. Let me look at some processes that happen when a device go on the network, right? So in IPv6, they ain't got the R process and they ain't got broadcast packets, right? You got this enable solicitation. This is one process, enable advertisement, router solicitation, router advertisement, and duplicate address detection. So like how you got ARP and IPv4, you got some equivalent but different processes. All right. So neighbor solicitation, neighbor advertisement, router solicitation, router advertisement, duplicate address detection. So let me learn a little bit about it. So before, let me show you the IPv4 equivalent. So this is your computer. You want to reach the next computer here, you got the next one there. So I go through back the ARP process here. Look at ARP is an important process. So he connect here to he, connect here to he. This is your switch, right? So this is a computer. So you build your packet now. 192.168.1.2. This is source IP. 192.168.1.3. This is your destination IP. And your source MAC now. Source MAC is, let me say, F. And your destination MAC address. F, let's say AA. Destination MAC address you don't know, right? So when you don't know the destination MAC address now, then you initiate the ARP process, right? The ARP process. So in the ARP process, what you do, set your source MAC address to your original source MAC address. And then the destination MAC address, you're gonna set it to all Fs. And then you're gonna ask the question, who has IP 192.168.1.3? And when the switch, right? So this is your switch. When the switch receives this broadcast packet, right, it's gonna send it to all the different devices. And each device receive it, each device check the message, and then the device which actually got the IP 192.168.1.3, he can answer back and he can say, well, this is me MAC address, right? He can answer back to this device and he can say, well, this is me MAC address, BB:BB:BB, and so on, right? So that's the ARP process. Now, what we're saying is that in IPv4, you got ARP, but IPv6, they don't use ARP. So what do you use in IPv6? Neighbor solicitation and neighbor advertisement, right? Give me a sec. All right, yeah, I'm good. Let me go. Start go. All right, so let me explain what's the neighbor solicitation. So the neighbor solicitation process. So we're doing the same thing. Find MAC address of the neighbor router. So the node, right? This is it got this IP address 2803:E340::1/64, right? So let me just explain this address to you. E340::1/64. So this address is 2803, and then you start with zeros. So there's 1, 2, there's 4, 5, 6, 7, 1/64, right? /64. So the network part, right? The network part is 2803, 16, E3 40 toward 2, 0, 48, 0. Right? So this is, so now, this is the network part. And the host part is 0, 0, 0. This is the host part. Right? So this is what this address is. So just like here, it's got your 192.168.1, that's 0/24, and the /24, that means that this part fixed. Similarly, your /64 means the first 64 bits fixed. So this is your network part. This kind of change. All right, so we go. So in figure 1, now this figure, you got this host, he wants to send a packet to 2803, E340, 2/64, but you don't know the MAC address. If it was IPv4, you would have sent a broadcast a ARP message, right? Instead, what you do is that you can construct a neighbor solicitation message to this IP, right? The source IP address gonna be his own address, right? 2803 E340::1. But the destination IPv6 address is a special IP address. It's not a broadcast address like in IPv4. It's what you call a solicited node multicast address. All right. Now, what's the solicited node multicast address? So node B, this device, the IPv6 address is 2803 E340:2/64, right? Good. The solicited node multicast address, you calculate it as follows, right? This is how you calculate it. So the first 104 bits, can't remember IPv6 address is 128 bits, right? The first 104 bits is FF02::1 FF00:0, right? It's a long address. Don't stress over it. So how much more bits to make 128? 24. So how you determine the last 24 bits, right? Now remember you're only doing this here, right? I want to explain this so you get an appreciation for the process. When you're configuring these things, this process is happening behind these things. But we want to understand how it's working so we can troubleshoot and know what these things are. So the last 24 bits, right, is 00002. So you take this, right? You take this, right, from the last 24 bits in the IP address, in the IPv6 address for node B, right? So when you take this first 104 bits, and when you take this last 24 bits, and you get this from the last 24 bits in the IP address, then the solicited node multicast address is FF02::1. Now you see the second colon here, this is a problem. This shouldn't be here. FF00:2, right? And then you got a rule for the computing the destination MAC address. It's 3333 FF, and then you take the last 24 bits of node B again, which is this. So now, right, he can send a neighbor solicitation message. The source IP can be 2803 E340::1, and the destination IP gonna be this IP address here, right? It gonna be this IP address here. So you might ask yourself, well, when this go out on the network, how node B gonna know that this message is for he, right? How he gonna know this message is for he? And how we know this? As soon as you configure 2803 E340::2 on node B, at the time that you configure, he does join a group, right? He can join one of these multicast group now is he solicited node multicast IP based on the IP address that he get. So when this message comes to he now, he can respond, he can answer back. And he can say, well, hey, look, this is me. I got this IP address. And this is me MAC address, right? So instead of a broadcast message that go to everybody, it uses the neighbor solicitation and the neighbor discovery. So two, neighbor solicitation and neighbor advertisement messages. Now, duplicate address detection is straightforward. As soon as you configure IP address on a device, you can send out a message to the rest of the network. So he can send a message to he owns solicited node multicast IP and ask any other device on the network whether they got the same IP address. If nobody can answer, then he know that he alone got this particular IP, right? So this duplicate address detection. All right, so here what the last thing I can do, because I want to leave early today, is talk about router advertisement and router solicitation. Let me just take 2 minutes break and then I can talk about this, right? It's not long. Just finish this and then I'll finish off. Any questions so far?
Not right now, sir.
All right, the last thing is the router advertisement and router solicitation message, right? So let me explain to you what is happening. The idea with IPv6 is to make things operate fast, right? So we got a network like this. So we got, let me say we got a device here. We got router here, router 1, and router 2. And then we get host 1. Good. So host 1, he got no couple of things, right? He command the network to connect a cable to he, and so host 1 connect a cable to him, right? What happens? Host 1 want to get an IP and he want to start work, right? So host 1 now going to send out a router solicitation message. So basically, host 1 asking any router here, right? What network you got? You get there. Let's put it in simple terms, right? Any router here, what network you get there for me, right? Good. So what this router solicitation message is, right? He send a message to a special, right? Multicast address. And any router configured on the network will be listening, right, on this multicast address. So when he see this router solicitation message come to this special multicast address, he's like, hey, somebody looking for a router, right? And then the router will reply, hey, I'm here, and my network is 2803 E3 Farte ::/64. Right? That's what he can reply and say. And then the host one will now, right, construct an IPv6 address. So he can take 2803 :E3 Farte as the first 64 bits. And the last 64 bits now is the EUI 64 address. And remember, this EUI 64 address is automatic based on the MAC address. So then this router now gets the IP address. And what you have to do, you don't have to do nothing, right? You don't have to do nothing. You just connect the device and this process work. The alternative is, right? The alternative is routers, right? The router can send out a router advertisement periodically. So in other words, he doesn't wait for anybody asking, if I on this network, right? He can send out this periodically and see if anybody wants an address. Like, hey, I on this network. Next 200 seconds, hey, I on the network. This is me network, like that. Now, when you got two routers on the network, right? Then you gotta get some priority. So router 2 might send out a message with a certain priority. Router 1 send it out with a certain priority. Whoever get the higher priority, does what they're gonna use as the network. So two routers on the same network, a little more complex. You gotta worry about that. Just when one router on the network, that's what you gotta concern yourself with, right? So does the router advertisement and router solicitation message. So IPv6 design could be easy and solve a lot of the problems that we had in IPv4. So tomorrow we can do a basic IPv6 lab with static routing, right? We're not gonna do OSPF with IPv6, there's OSPF v3, and then we start talking a bit about BGP. So those are all that we want for
tomorrow.
So yeah, so tomorrow we get the class.
So, all right, so I joined a bit late. I know we talked about.
Yeah. The class are going to fill you in. Tomorrow from 5:30 we can reach and see if you could close off at 7.
There's online?
Yeah, online.
Oh.
Right, we not get class Thursday. Just for this week, yes.
Right.
All right, so come prepared with packet tracer tomorrow. And we can build some networks, right? All right, that's it for today.
Sure, you pose this lecture notes.
No, we post election notes yet. Here we go.
All right, I use the book then. All right.
Yeah. We gotta do what I'm post election notes, right? I know a little back with election because it's enough thing. And
No,
you know,
but I remember
copy and
Terry that
paste.
you're working on it and you can use the book.
Yeah,
anytime.
because it's first time doing the course, so the election notes. I just want to tell you this whole chapter and then send it to you, right? I just go through it and then take from different sources and then put it together with piece thing, right?
Answer.
Yeah, I'm pushing to get it through to you though. When you get it sufficient time before your exam.
Correct.
Yeah. All right, good. That's it for this class. Assignment, remember Thursday you submit your assignment, right? You got till the end, your lab. You got till the end of the day, 12 o'clock midnight, so email it to me. And then you'll get the second one and give you on static routing to do on Thursday, right? And upload it to.
Tomorrow, I mean.
No, Thursday.
Following week. Okay.
Thursday. Yeah, Thursday June. And Thursday I'm gonna send the next one to you. Tomorrow is just normal class.
Okay.
All right, good. Listen.